Hey everyone, and welcome to This Explainer. Today, we're talking about the invisible traffic rules of Ethernet. Every single day, we're sending billions of messages, streaming 4K video, hopping on video calls across the globe, and we do it all without a second thought. But right beneath the surface of this seamless digital life we all take for granted, there's an invisible, incredibly chaotic world of data traffic going on. Today, we're going to pull back the curtain and uncover the unseen engineering rules that actually allow our devices to talk to each other. We're going to see exactly how engineers manage to take a literal digital Wild West and turn it into the highly structured, hyperspeed networks we rely on today.
Okay, let's dive right in. To truly appreciate how good we have it right now, you really have to understand the total nightmare that was early computer networking. I want you to imagine a world where every single car in a massive city has to share one gigantic multi-directional intersection. No traffic lights, no stop signs, and everyone is blindfolded. Yeah, that is essentially what early networks were like, just the recipe for a massive, continuous, multi-lane car crash. So engineers were faced with this completely monumental task. How in the world do we stop these digital collisions and build the smooth, orderly highways we actually need?
Now, to try and fix this chaos, early network engineers did what engineers do. They established some strict traffic rules for these devices to follow. But this actually led them straight into a deeply frustrating physical engineering problem. And that brings us to the central question of our explainer today. Think about this for a second. If every single computer on a network perfectly follows the communication rules, why do the networks still crash? Keep that question in the back of your mind as we go, because answering it, that's exactly what drove decades of brilliant networking evolution.
So to answer that question, we really have to look at the physical root cause of the problem. And this brilliantly illustrates the fundamental challenge of what's called a shared medium. You see, early Ethernet was literally just a single shared copper wire. Just one long physical tube connecting multiple workstations together, a multi-point system. What that meant was, if two workstations decided to transmit their electronic signals at the exact same fraction of a second, those electrical impulses would physically travel down the wire, violently collide right in the middle, and be totally destroyed. It wasn't a software bug, it was a purely physical limitation.
Right. So the crucial point here is that engineers desperately needed a system to manage this shared space. So they came up with a foundational set of traffic rules, a sort of, brilliant digital band-aid. They called it CSMA/CD. That's a mouthful. It stands for Carrier Sense Multiple Access with Collision Detection. Let's actually break down how this mandated network behavior. First up, carrier sense, meaning before a computer can even try to talk, it literally has to listen to the wire to see if it's empty. Makes sense, right? Next, multiple access. This means every single workstation has equal rights to jump in and use that wire when it's free. There's no boss telling them when to go. And finally, collision detection. Devices have to actively keep listening while they're talking. If they detect that the signal they're sending out is getting garbled by someone else's signal, they immediately stop. So, listen first, share equally, and stop if you hit something. Sounds totally foolproof, doesn't it?
Well, not quite. Actually, what's really fascinating here is why collisions were completely physically unavoidable, even with those perfect CSMA/CD rules in place. Take a look at the first scenario. Sometimes the wire is completely silent, right? And two computers check it at the exact same millisecond, t equals 0. They both think, awesome, it's clear, and boom, they transmit simultaneously, giving us an immediate crash. But the second scenario is even wilder. It comes down to spatial propagation delay. Electronic signals travel super fast, obviously, but they aren't instantaneous. It actually takes physical time for a signal to travel down a long wire. So say computer A starts talking. A tiny fraction of a second later, computer C checks the wire. Because A's signal hasn't physically reached C yet, C thinks the wire is empty and starts talking too, and boom again. Another totally unavoidable crash, dictated purely by the laws of physics.
So, since collisions were just an absolute reality of the system, networks needed a standardized post-crash recovery process. Basically, a way to clean up the mess and try again without just causing another massive pileup. Here is exactly how that worked, in 3 steps. First, the absolute split second a collision is detected, the computers involved broadcast a 32-bit jamming signal. They are essentially screaming, "Stop," down the wire to halt everything. Second, this triggers a forced back-off period. Every station goes into a brief holding pattern to avoid total gridlock. And third, and honestly, this is the genius part, they wait a random amount of time before trying again. It's literally like rolling digital dice. Because the wait times are completely random, the chances of those two computers waking up and colliding a second time are drastically reduced.
Now, when you map all of these rules out, You get the complete decision logic loop of early Ethernet. And looking at it really highlights how network communication back then was just this highly stressful, continuous cycle. You check the line, you transmit, you literally cross your fingers hoping you don't crash, and if you do, you send a jam signal, back off, wait a round amount of time, and loop right back to the very beginning. It was this crazy, dynamic balancing act just to get a single piece of data from point A to point B. And as you can probably guess, as networks grew, this constant loop of trying, crashing, and waiting, it became a massive bottleneck. Efficiency was just plummeting.
Okay, so let's move to the next major leap in our story and see how this actually builds into the modern technology we use today. The shared wire had totally reached its limit. We needed a game-changing architectural shift, and that arrived with the network switch. Instead of having all the computers sharing one massive, chaotic broadcast line where everyone hears literally everyone else, the switch comes in and acts like a highly intelligent traffic cop. It physically cuts up the network into isolated blocks, or what we call segmented collision domains. Now, if computer A wants to talk to computer B, the switch handles it directly. The rest of the network doesn't even hear a peep. That chaotic single lane was finally divided up into precise, separate intersections.
But here's the catch. Introducing a smart switch meant that the switch itself now had to make decisions, and it had to make them unbelievably fast. We are talking about the microsecond dilemma. Every single time a packet of data enters that switch, the switch has to instantly decide what to do with it. Does it immediately forward the data as fast as physically possible to keep latency super low? Or does it take a tiny bit of extra time to read the entire package and check it for errors to ensure perfect accuracy? You literally cannot have both. Speed and accuracy are fundamentally at odds here.
So let's look at the 3 specific routing strategies a switch actually uses to solve this dilemma. First up, we have fast forward. This is pure, unadulterated speed. The switch reads just the first 14 bytes, literally just enough to read the destination address, and instantly kicks the data out the right door. You get the absolute lowest latency, but zero arrow checking. Then in the middle, we have the compromise, fragment-free. This one reads the first 64 bytes. Why 64? Well, mathematically, if a collision happened, the resulting fragmented data is almost always smaller than 64 bytes. So it's a clever, low-latency way to filter out the most common errors. And finally, we have store and forward. This is the ultimate vault. The switch takes in the entire 1500-byte frame, runs a full mathematical check on it, and only forwards it if it's 100% perfect. Highly accurate, but it definitely introduces the highest latency.
And seeing these laid out brilliantly illustrates the harsh reality of network engineering. There is no such thing as a perfect mechanism. Never. There is always a strict trade-off. As you increase your error filtering capacity, you inherently increase your delay, your latency. Network administrators actually have to sit down and choose the right physical decision based on what their specific network needs at that exact time. If you're running real-time voice calls, you probably want fast forward. But if you're transferring highly sensitive financial data, you absolutely want store and forward. It's a really delicate, deliberate balance.
Now, the switch was obviously a massive improvement. But to truly permanently solve our original traffic crash problem, we needed to upgrade the road itself. And this brings us to the massive transition from half-duplex to full duplex. Half-duplex is what we've been talking about this whole time, the old single shared tube. Data can go both ways, sure, but only one direction at a single time. Full duplex, though, that is the ultimate evolutionary step. It's the divided highway. It entirely replaces that single pipe with 2 completely dedicated, totally separate tubes, one exclusively for talking and one exclusively for listening.
And honestly, it is so easy to see why this architecture was completely revolutionary. In a full duplex network, you have your transmit line sending data out and your receive line bringing data in. Because these are physically separate pathways, bidirectional flow can happen simultaneously. You can finally talk and listen at the exact same moment without any fear whatsoever of your signals crashing into each other. The physical environment that caused all those collisions, it has literally been engineered completely out of existence.
So what does this actually mean in the real world? The impact is staggering. When you move a network from a 100 megabit half-duplex connection over to a full duplex connection, you don't just stop the crashes, because you can now send 100 megabits out and receive 100 megabits in at the exact same time. You perfectly double your physical bandwidth. Just like that, the link instantly becomes capable of handling 200 megabits per second. It was an absolute game changer for network performance.
Which actually brings us right to the climax of our Ethernet story. In a modern network, utilizing these powerful switches and dedicated full duplex lines, we have finally reached a collision-free utopia.
Every single computer has its own private 200 megabit two-way highway directly to the switch. And because physical collisions are now practically impossible, those original foundational rules we spent all that time talking about, CSMA-CD, the listening, the waiting, the random dice rolling, they are completely 100% obsolete. The network has totally freed itself from those early physical limitations, finally allowing for maximum unhindered efficiency.
It's just amazing to think that the backbone of our modern internet was once managed by devices literally rolling random dice just to avoid electronic car crashes. It really leaves you wondering, as technology continues to sprint forward, what other invisible digital band-aids and legacy workarounds are hiding just beneath the surface of the tech we use every single day? What else is quietly keeping our modern world running without us even noticing? Thank you so much for joining me on this explainer. Keep asking questions, and I'll see you next time.